Hello. In previous lectures, we were discussing thermodynamics, and we started along with the first law of thermodynamics. And today we are going to continue a little bit further and see what are the applications of first law of thermodynamics. And we will also find an expression which is called as the Mayer's relationship in today's class, and for van der Waals gases and for ideal gases, both of the cases. And let's see how it goes. So we've already, I hope we've done 3 of the delta equations. And I think today is the right time to switch over to this topic, which is the applications of the thermodynamics. And first law of the thermodynamics. Let us begin without wasting time. Just give me a minute. Okay, just give me a minute. Okay. So what we have done so far, let me just check it so that I start along with that only topic. Okay, so we have done in the previous class the heat capacities and the 3 different delta equations. And today let us start with the applications of first law of thermodynamics. And specifically, I'll start with something called as the Mayer's relationship. Okay, so let us start today. So you might have seen that your internal energy is the state of the system. And since it is the state of the system, it depends on the state variables like T, V, and T. And it also depends on initial and final points and doesn't depend upon the part taken. So, so what we can do, as we've seen, that thermodynamic variables can be represented on the PVT space. So it can be represented on the PVT space. Similarly, the internal energy that we studied uh, in the postulate of the in the postulate of first law of thermodynamics, we studied that internal energy is a state variable, and like pressure, volume, temperature, it also can be represented by a point in PVT space. So it can be represented by a point in PVT space. Okay. So for instance, what I'll do, and also we have studied a different expression of first law of thermodynamics, where you can have some, if you add some number of particles, then you have a different kind of first law of thermodynamics. I'm sure I have already taught all those things. So in the absence of diffusive interactions, in the absence of diffusive interactions, I hope I'm audible. So in the absence of diffusive interactions, so in absence of diffusive interactions, I can write my first law of thermodynamics, that is the heat added to the system, can be represented as the sum of the change in the internal energy plus PdV. And this heat can be given to a system in an isobaric way, that is at a constant pressure. It can be given at a constant pressure. Sorry, this heat can be given at a constant pressure, and it will also be given uh, at a constant volume. So accordingly, we'll have 2 different heat capacities, which will have heat capacities defined at constant volume and defined at constant pressure. So there will be 2 heat capacities that would be talking of, one defined at constant volume and other defined at constant pressure. So we have 2 kind of heat capacities, one at constant volume, other at constant pressure. So let us assume for simplicity that we are talking of, let us assume of 1 mole of gas. So we are assuming 1 mole of gas so that life becomes a little easy for us. And let's say it is contained in a container fitted with a piston. Container fitted with a piston. So let us consider a case of 1 mole of gas contained inside a container fitted with a piston. And now we have now as we know that internal energy can also is a state function, so it can be written in terms of state variable. Let us say that it is a function of both t and v. Now, if I write t du, it will be equals to del u by del t at a constant volume times dt plus del u by del v at a constant temperature dv. And similarly, I can write my del q. Now, if I replace this du in my first law of thermodynamics, in the first law of thermodynamics, in the absence of diffusive interactions, if I take that case, and if I write my delta q will be equals to del u by del t at a constant volume times dt plus p plus del u by del v at a constant temperature dv. And what I'll get, this is the new expression of delta Q when I'm expressing my internal energy as a function of T and V. I have already stated three delta Q equations in the previous lecture. So it is one of those delta Q equation. Okay. Okay. So now one way of imagining all these things can be, I can imagine that piston is tightly clamped. So I can imagine my piston is tightly clamped. And when it is tightly clamped, so gas cannot do any work, cannot do any work. And since gas cannot do any work, all the heat that goes, it is going to increase the internal energy of the system. So all the heat is going to affect the internal energy and is only going to increase the internal energy of the system and therefore the temperature. For ideal gases, if I'm talking for ideal gases, I've already told that internal energy happens to be the function of temperature alone. Now we will come to a point that is heat required to raise the temperature of 1 mole of gas by 1 degree when its volume is kept constant. When its volume is kept constant is termed as the molar heat capacity at a constant volume. Is molar heat capacity at a constant volume. So it is called as the molar heat capacity at a constant volume. So what is CV? CV is nothing but it is equals to delta Q by delta T, or I can write dt at constant volume. And obviously, at constant volume, this dV terms become 0. So sorry about this, P plus. Okay. Okay. So at constant volume, if I'm talking constant volume, the dV terms become 0. And I can simply write that this is equals to del U by del T at a constant volume. So my CV is nothing but del U upon del T at a constant volume. And what is CV? I'm representing my CV here as I told you in the last lecture. We can say molar heat capacity, we can say specific heat capacity. Here I've taken number of moles equal to 1. So I'm dictating it as a molar heat capacity. So CV happens to be del U by del T at a constant volume. And in particular, I can write my small CV. This is called as a specific heat capacity, and specific heat capacity is nothing but it is equals to at a constant volume. I can the specific heat capacity is as you can say CV upon total mass. Okay, so this is how I can define my specific heat capacity. Okay, now suppose there's another way in which we can raise that heat, and that can be when piston is allowed to move. Let us say piston is allowed to move against constant pressure. So piston is allowed to move and the gas is subjected to a constant pressure. So I'm talking of gas expansion under a constant pressure. Now, in this particular scenario, some of the heat ends up as mechanical energy of the surroundings. So no longer we can say that work done is non-zero. So work done is 0. So here, some part of heat will be will end up as mechanical energy of the surrounding. So in order to achieve the change in temperature, more heat is to be supplied in the constant pressure process. So when I'm talking of constant pressure, so more heat is to be supplied, because now here work done cannot be zero. Okay, is that fine? Now molar heat capacity I can define at a constant molar heat capacity of a gas at a constant pressure. At a constant pressure is defined as the amount of heat, can be defined as the amount of heat required to raise the temperature of the gas by by temperature of gas, or I think I can write 1 mole of temperature of 1 mole of gas by 1 degree. Okay, the heat required uh, to raise the temperature of 1 mole of gas by 1 degree at a constant pressure. Okay, at a constant pressure. At pressure constant. So if I'm talking of constant pressure, then it implies that, sorry, molar heat capacity at a constant pressure is defined as the amount of heat required to raise the temperature of 1 mole of gas by 1 degree Celsius. Then it will be equals to delta Q by del T at a constant pressure. If I'm talking of this, now no longer my PdV would be zero. So now I can write my del Cp, Cp, so my Cp would be equals to what? So now let me let me just take a little bit of time. Sorry, what was delta Q? Delta Q was nothing but it is equals to du plus PdV. So now my PdV is not zero, and my internal energy I can write, uh, what I can write? I can write it as, let's say I'm taking as u as a function of T and V again. So what I'll get simply del u upon del T at a constant volume dt, del u upon del V at a constant temperature dV. So this is one thing that I know already. Okay, so this is something that I already know. And what I can do is, I can simply do is, this is my u. Okay, so last time what did I write my u? Acha, that time PdV became zero. So it is del u upon del T at a constant volume is simply Cv. Now I'm trying to write, trying to write Cp. Okay, so this is my equation number 1. And how can I write my another equation? So I think I should write it in a manner, since I'm talking of constant pressure. So volume, I should write it a constant pressure, then it becomes, so it's instead of, okay. So let me write my del u at delta Q by delta T at a constant pressure would then be equals to what? It will be equals to del u by del T at constant volume plus this particular thing. So I'll get simply, I'll write it here so that I'll get something. So plus T dV, but dV is here also. So some internal energy term will come here with D, and this will come as dV. And here I am differentiating with respect to time, so I'll simply write temperature, so I'll write simply temperature. But all these things at a constant pressure. Are you getting my point? So see, there is a term of PdV involving differential volume, and then there is a term of differential volume here as well. So I have added these two terms. And since I'm evaluating del Q by del T at a constant pressure, so this dt comes down. When it comes down, so basically the EV by dt at a constant pressure. So I think this is something that I know. So this is my Cp. So what is my Cp? Cp is simply, I'll write it here on the better side. So Cv already I know. Cv is del U by del U by del T at a constant volume, while Cp is del U by del T at a constant volume plus P plus del U by del V at a constant temperature times del V by del T at a constant pressure. Okay, so this is something that one must know. Now, what would be my Cp minus Cv? So my Cp minus Cv will be P plus del U by del V at a constant temperature times del V by del T at a constant pressure. So this is one of the central themes you should keep in mind. Okay, so this is an important equation that you should keep in mind. Okay, now what will happen? Now we'll see this case for two different scenarios. One would be your perfect ideal gas. So in an ideal gas, what happens is, so let's say if I've kept my number of moles to be equals to 1, so this is all evaluation at number of moles equals to 1. And the ideal gas equation happens to be PV equals to nRT, but here simply is this PV is equal to RT. And secondly, when I'm talking of ideal gases, I'm talking of no intermolecular forces. So I don't have any intermolecular interaction here. So no intermolecular interaction. Since I'm talking of no intermolecular interaction, it implies that internal energy of a perfect gas is completely kinetic energy. So it's completely kinetic energy. The potentiality term will become zero. So is completely kinetic. And so I can say that my potential energy between two gas molecules depends upon the volume. So my del U by del V, it turns out to be zero, because the internal energy is completely kinetic and there are no intermolecular forces. So the interaction term would be zero, and interaction term would depend upon the volume basically. So the del U by del V term, del U by del V at a constant temperature, this term becomes zero. So what happens is my Cp minus Cv turns out to be P times del V by del T at a constant pressure, specifically for ideal gases. Now for ideal gases, this is the case. And for ideal gases, if this is the case, I already know my volume is nothing but it equals to n RT upon P. And P is constant, so P cancels P. So del V by del T will be equals to R upon P. Now replacing this in this equation, I get del V by del T at a constant pressure will be simply equals to R upon P. So Cp minus Cv turns out to be equals to R. This is called as the Mayer's formula. And this formula is quite successful, or holds rather well for monatomic gases. So for monatomic gases, this holds quite well. Monoatomic gases. So for monoatomic gases, it holds quite well. But for polyatomic and diatomic gases, a fair reasonability can be expected. So for uh, for polyatomic and diatomic gases, I can say that it is fairly reasonable, but it holds good for monatomic gases. So this is one of the things that I wanted to produce. Second thing is, if I wanted to find what about the van der Waal gases. So in van der Waal fluids or van der Waal gases, let us gases, the internal energy is a function of volume, because now here we cannot forget the forget what we cannot forget the intermolecular interaction. So now internal energy is function of volume, And the equation of state for 1 mole of gas, 1 mole of van der Waals gas, a van der Waals gas ni 1 mole of gas following the van der Waals equation would be P plus A by V square, V minus B is equal to RT. So this is the equation of gas. Okay, here A and B are constants for the gas. Internal energy is already given by, I think this I already know. So let me write it as, again, let me write it as, so U is equal to what? Minus A upon B plus some constant K. So this is equation number 2. So clearly now we can see that del U by del V at a constant temperature is not zero, rather it is A upon V square. So this is equation number 3. Now clearly Cp minus Cv, which is equals to, it was equals to what? It was equal to P del V upon del T at a constant pressure. Now, instead of this, because we are talking of van der Waals gas, so I'll replace this. So it will be Cp minus Cv is equal to P plus, I think A by V square I should write, times del V upon del T at a constant pressure. This is my equation number 4. And from 1, so basically this equation I can use again. So if I want to obtain this del V upon del T at a constant pressure, how will I obtain? Okay, so I hope this is clear now. So instead of P, I will get this term now. P plus A by V square. See why? If you're actually having certain troubles, then let me get back to the thing. Okay, so this is why. Because no longer this term is 0. So this term was 0 otherwise, but now this term is not 0. So I'm just adding this term in van der Waals equation. In van der Waals, this is from here. So this basically I'm trying to write here that instead of P, we'll have P plus del U by del V term also added. And this P plus del U by del T term will result in the same term, which is equals to P plus A by V square. So I hope it is clear. Okay, so now how to generate this? I think this term. So I have to generate this term. No? Okay, so what I'll do, I will, so sorry, I will simply differentiate this equation number 1. So if I differentiate this equation number 1 with respect to temperature, with respect to temperature, what would I get? I will simply get P plus A by V square del V upon del T at a constant pressure plus V minus B minus 2A by V square del V by this is multiplied. So at a constant pressure is equals to R. So this is my equation number 5. It's so complicated. So let me just write del V by del T at a constant pressure. It is equals to, mm, I should write it here. Yeah. So I'll write P plus E upon V square del V by del T at a constant pressure. This entire thing is equals to what? How to write this? I think this is quite complicated. Just give me a minute, okay? So just give me a minute. Okay, so what was I doing? So let me just do a little bit calculation here. Mm, so Cp minus Cv will be simply what I can do. I can do one thing. So I'll do this thing. Del V by del T at a constant pressure is equal to what? It is equal to R upon P plus A by B square minus 2A by, so sorry, it is V cube, I think. 2A by B cube, V minus P. So this is another equation. Okay, so what I can do, I can replace this here. I will replace it by, at this point. So what I'll do, I'll simply write Cp minus Cv. So Cp minus Cv is nothing but P plus A by V square into R upon, I think this is quite complicated now, T plus A by V square minus 2A by V cube R minus P. So this is for non-ideal gases. So for basically this expression is for van der Waals gases, where your internal energy is equals to minus of A upon B. So now internal energy depends upon volume. So no longer your del U by del V would be zero. So now I'll add this and add this particular term, that is del U by del V at a constant del U by del V at a constant pressure, I think. So that term would be added here. So I hope it is now clear. So this will be your new term. Now a little bit of approximations can be tried. So Cp minus Cv, I'll write it here, turns out to be R P plus A by V square divided by P plus A by V square minus 2A by V cube. And then you have again V minus B. What I can do, I can divide it here. So it will be like Cp minus Cv is equal to R divided by 1 minus 2A by V cube V minus B divided by P plus A by V square. Or then we can do one thing. Hmm, what I can do, now I can use the van der Waals gas, that is P plus A upon V square into V minus B is equal to RT. So I can simply write P plus A by V square is equal to RT upon V minus B. So I can use it here. So what I'll get, I'll simply get my Cp minus Cv is equal to R upon 1 minus 2A by V cube and RT upon V minus B. So basically I'll write RT upon V minus B. So this will become V minus B whole square. And then I'll get simply RT here. So I think this is more than sufficient. And a little bit of approximation we can try. We can write, because we already know that A and B are very small. So what I can do, I can simply write my Cp minus Cv is equals to R upon 1 minus 2A. And this, because B is very small, so this will, I'll simply approximate it by V square only. So this will give me 2A upon VRT. So this is my, this is my modified kind of Cp minus Cv. For ideal cases, we don't have A. A is 0 there. So then you can simply write Cp minus Cv is equal to R. But for van der Waals fluids or van der Waals gases, I'll write Cp minus Cv. I can also use binomial theorem. So I'll write 1 plus 2A upon VRT. So we know that 1 plus x raised to power n is equal to 1 plus nx. So I have simply replaced 1 minus x as simply, so basically I have written as 1 upon 1 plus x. So 1 plus x raised to power minus 1 I can simply approximately write it as 1 minus x. So this is what I've done. So Cp minus Cv can be approximately written as R times 1 plus 2a upon BRT. And now let's say let us define a few more things. Let us define that let's say Kt is my bulk modulus. Kt is my bulk modulus, and alpha, let's say it is a coefficient of volume expansion. Let's say coefficient of volume expansion is alpha. Then you can rewrite this expression. I'm leaving it for you. Cp minus Cv as simply minus T del P by del T at a constant volume and del V by del T whole square at a constant pressure. And you can write this entire thing as, I'm leaving this as a homework for you. You can do it on your own. So it will be equals to Kt alpha square into B. So this is a more general relationship. More general sort of relationship. That is Cp minus Cv can be more generally written as Kt alpha square times B. Okay, so this is one of the things that I've already done for you. I think these are easy things to do. So therefore, I'm not laying much stress it here. But see, with all these new things in place, what you can do, you can also rewrite your first law of thermodynamics. We have written first law of thermodynamics for simple cases, that is for just gaseous system, that is I have written it as delta Q is equal to du plus PdV. Then in case of presence of diffusive interaction, I can add this term, mu is the chemical potential. Okay, now I can write my first law of thermodynamics by the help of these two new Cp's and Cv's. See how? I already know that my delta Q, according to first law of thermodynamics, it is equal to du plus a PdV. So it is equals to du plus PdV. Now what I can do, I already know that my delta U by delta T at a constant volume is Cv. It is equal to Cv. So what I can write, my delta Q is equal to simply Cv dt. I can write my delta U is Cv dt plus PdV. So if I want to express my first law of thermodynamics with the help of these molar heat capacities at a constant volume, I can write delta Q is equal to Cv dt plus PdV. And if I use the equation of state for an ideal gas, I know that PV is equal to simply RT. So PdV plus VdP simply equals to RdT. And from here, I can simply write my delta Q, which is equals to Cv. So instead of Cv, I can write Cp plus R dt. And instead of PdV, I can simply write RdT minus VdP. So I'll write simply this. Oh, my bad. See, what I can do, what I wanted to express was, see, I wanted to express that delta Q is equals to what? It is equal to Cv dt plus PdV. And I already know that my PdV plus VdP is equal to RdT. So instead of PdV, I can write what? I can write RdT minus VdP. Okay. So what I can do, I can write simply my delta Q is equal to Cv plus R times dt minus VdP. So in terms of molar heat capacity at a constant pressure, I can write my first law of thermodynamics is in this fashion, that delta Q is equal to Cp dt minus VdP. So this is how I can rewrite my first law of thermodynamics. For ideal substances, for more generally, this is the expression Kt alpha square V, where Kt is the bulk modulus, alpha is coefficient of volume expansion, V is volume. So this is how I can also express Cp minus Cv. I have already calculated Cp minus Cv for ideal gases and for wonderful gases. This is something I'm leaving for you as your homework. Try to find it in your books and try to try to derive it. And this is how I can express my first law of thermodynamics when I have to do this first law of thermodynamics for when I have to write the first law of thermodynamics using the molar heat capacities at a constant volume and at a constant pressure. So now, in the next lecture, I'm going to introduce you something called as the adiabatic equation and the enthalpy. Okay, and in the next lecture, we'll try to also finish some topics regarding entropy. Okay, so till then, I hope we have done a little bit enough, and I also urge you that you should revise a little bit of your Carnot cycle of your 11th standard. If you remember whatever you have done at your 11th standard, it will be nice for me to introduce you the concept of the Carnot cycle. And also you might know from your standard 12th what is equation of state for adiabatic process. So adiabatic process, the equation of state is PV raised to power gamma is equal to K. If you remember, PV raised to power gamma is equals to K. And so for a thermally isolated insulated system or for adiabatic system, you know that delta Q is equals to 0. And your equation first law becomes du is equal to minus dw. That is why I'm using d here, because along all adiabatic paths, your work done is no longer a path function. It becomes a state function. It is equals to du. Okay. So decrease in internal energy of a thermally insulated system is equal to the work done by the system. And increase in internal energy is equals to the work done on the system. So increase in internal energy implies work is done on the system. Since du depends on the initial and final points, the work done in adiabatic process is also independent of part taken. So when I'm talking of work done in adiabatic process, it becomes independent of part taken, and therefore it becomes a state of the function, it becomes a thermodynamic state of the system, because then dw is called by a special name called as a change in the internal energy. And since u is a function of T, a fall in internal energy implies a decrease in the temperature. And when we are talking of adiabatic compression, work is done on the system, so the temperature increases. So I'll write it here. When I'm talking of adiabatic expansion, so work is done by the system. So for that, if dw is positive, it implies du is negative. If du is negative, it implies that internal energy decreases. Internal energy decreases means drop in the temperature. And when I'm talking of adiabatic compression, so adiabatic compression means dw is positive. Dw is negative, because dv compression in compression case dv is negative. So dw is negative. When I'm doing compression, it implies work is done on the system. So work is done on the system is negative, 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 positive. So work done on the system means dw is negative, 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 positive. It implies du is positive. It implies u is increasing. It implies rise in the temperature. So I hope this is clear to you. Okay, this is clear to you. Now, suppose we are taking the case for 1 mole of the gas. Suppose for 1 mole of gas. So suppose 1 mole of gas is subjected to a quasi-static adiabatic expansion. So we are subjecting 1 mole of gas to quasi-static adiabatic expansion. Okay. And we already know that delta Q can be written as CV dt plus PdV, or you can write it as Cp dt minus VdP. I'm using CV dt plus PdV. Okay. During expansion, if I'm talking of quasi-static process, so during expansion, what happens that there are infinite equilibrium state is deviating slightly away, but otherwise, for an ideal gas, I can write that equation of state will hold good for all intermediate states. So for all intermediate states, I can write for all intermediate equilibrium states, I can write that PV is equal to RT will hold good. And that implies that I can write P is equals to RT upon V. I can write pressure is equals to RT upon V. And if I write pressure is equal to RT upon V, what I'll write for adiabatic case, I already know that for adiabatic case, I already know my delta Q is equal to 0. It implies CV dt plus, instead of P, what I can write? I can write RT upon V dV is equal to 0. And from here, I can write that dt upon T will be equals to minus dV by V. And then there would be R also, and there would be CV also. If I integrate it, I'll get ln T is equal to minus R upon CV ln V plus ln K. And so from here, I can write T R CV ln is equal to ln K. So I'll get R into T. Have I written something wrong? No, so sorry, so sorry. So sorry. Not this. It will be equals to what? So sorry. So what it will be equals to? What is happening? So it will be equals to what? It will be equals to what? It will be equals to ln T. This will come here. So it will be plus R by CV ln V is equal to ln K. So I can write T into V raised to power R by CV is equals to constant. T into V raised to power R upon CV is equal to constant. I think this is fine. Yeah. So T into V raised to power R by CV is equal to constant. So I can also write T for ideal gases. I know R, I can write it as Cp minus Cv divided by Cv is equals to R. So I can simply write, I can write Cp by Cv as some constant. This I'm writing it as gamma. So if I write this as gamma, so this will be T into V raised to power gamma minus 1 is equals to R. So this is an equation of state. This is an equation of state for adiabatic processes. That is when delta Q is equal to 0, TV raised to power gamma minus 1 is equal to R, where gamma is equal to Cp by Cv. And then you can do all sort of thing. You can replace, instead of V, you can write this as RT upon P. So if you write it as RT upon P raised to power gamma minus 1, this will be equals to this. So it will be T raised to power gamma and P raised to power 1 minus gamma is equals to some constant. So this is also equation of state. And from this, you can also derive PV raised to power gamma is equals to constant. So for adiabatic process, these are the respective equations of state. So while we derived it, one of the things that we was when we were concentrating, that we were talking of quasi-static adiabatic processes, that is between initial and final state, all the states are almost close to equilibrium states only. We have used an equation of state for ideal gas, that is PV equal to nRT, or PV is equal to RT here, because we have used the number of moles equal to 1. And since we have used ideal gases, we have only considered that the internal energy is proportional to the temperature. So for all these things, the adiabatic state of adiabatic state, or you can say that adiabatic equation state for adiabatic process happens to be PV raised to power gamma is equal to K, or TV raised to power gamma minus 1 equal to K. That is some constant. I think this is not R, this is some K only. I've made some mistake. Please see, this is K only. Okay? I think ln K it is. So it is ln K, not R. Okay. This is ln K, not R. Please write. Okay. Okay. So I hope all these things are done. So this is equation of state for an adiabatic process. Okay. So in the next class, we'll try to see a little bit more on this adiabatic thing, and we'll try to at least start with entropy, and at least start with entropy. Till then, take care. Bye bye.